Hello everyone, and welcome to part 4 of this 4-part mini-series on Archimedes and his mathematical innovations. In this video, we're going to be talking about his work, Measurement of a Circle. And unlike the last works that we've talked about, this one actually doesn't have an introduction, and so I'll just kind of explain it to you. In this, Archimedes is really trying to provide some information and in fact, he ends up finding an upper and lower bound for the ratio between the radius of a circle to that of its circumference. And so let's move right on into Proposition 1. So in Proposition 1, Archimedes says, the area of any circle is equal to a right-angled triangle in which one of the sides about the right angle is equal to the radius and the other to the circumference of the circle. He says, let ABGD be the given circle and K the area the triangle described. He then says, then if the circle is not equal to K, it must be either greater or less. So he's kind of proving it by trying to prove a negative. So he then moves on to, and he says, if possible, let the circle be greater than K. Inscribe a square ABCD and bisect, so inscribe a square and then bisect bisect the arcs AB, BC, CD, DA, and then bisect, if necessary, the halves, and so on and so forth. So we're creating a polygon on the inside there. And so on and so forth until the sides of the inscribed polygon whose angular points are the points of subdivision. So basically he's saying, what he says in the end here, thus the area of the polygon is greater than K. So basically keep making this until the area would be greater than K. And then if you do this, you can find the radius of your polygon right here. And we can see that that's actually shorter than the actual radius. And then we know that the perimeter is also going to be a little bit less. So we end up with this smaller triangle on the inside here, right? This orange is the area of the polygon. Well, the whole point of this was trying to say that the area of the polygon is greater than the area of the triangle, right? Or K here. And so clearly it cannot be less because this is showing that it isn't. He then says, if possible, let the circle be less than K. He then says to circumscribe a square and let two adjacent sides touching the circle in H meet in T. He then says to bisect the arcs between the adjacent points, right, like that right there, and draw the tangents and the points of bisection. Let A be the middle point of the arc, EH, and FAG the tangent at A. And so you can see, if you continue this on around the rest of it, you end up with an octagon. I'm going to stop trying to draw that because that doesn't work very well. But we're essentially creating yet another polygon. He then points out that your radius is still the same, right? That's the same distance there of your polygon, but that the area is going to be greater than the area of your perimeter. And so your area here in purple is going to be greater than the area of your triangle, which we just said we wanted the area of the circle to be less than K, and here it is being greater. So he then says, since the area of the circle is neither greater nor less than K, it must be equal to it. And so by proving that it's not greater or less than, he can say, clearly the only other option is for it to be equal. We then move on to Proposition 3 here. And this is really the meat and all of the math that he does. He says the ratio of the circumference of any circle to its diameter is less than 3 times 10 over 7, but greater than, 3 plus 10 over 7, but greater than 3 plus 1 over 7. So here he's trying to define the upper and lower bounds of this. And so to go about doing that, he says, let AB be the diameter of any circle, O its center, AC the tangent at A, and let the angle AOC be 1/3 of a right angle. So this right here is 30 degrees. We've got that. So this is the system that he sets up. He then bisects the arc and creates this new line here. And then he solves and he does the math, proving the ratio between this distance here and this distance here. And he does this for each of these different steps, but he does it again and then again. And he really just, each step, he proves and he finds that ratio there. Unfortunately, I don't have time to show all of that math. It's really fascinating. Feel free to go and take a look at it yourself. But he keeps doing this. And then if you take a look at it and if you do this all the way around, he says, therefore, the circumference of the circle being less than the perimeter of the polygon, which is 96 sides in this case, he says that it is a forte, or just less than 3 1/7 times the diameter of AB. And so he sets up this 96-sided polygon. He finds the ratio, and then he finds that it is 3 1/7. So that provides us with our upper bound. He then tries to define the lower bound. So he says, next let AB be the diameter of a circle, and AC meet the circle in C. Make the angle CAB equal to 1/3 of a right angle. So here's that there. Join BC. So he sets up this situation here. And then he keeps going through, defining in a very similar manner, right? Taking a step, solving the math, and then doing the next step, solving the math. He then says, therefore, BG is a side of a regular inscribed polygon of 96 sides. Much more than is the circumference of the circle greater than 3 10/71 times the diameter. So again, he takes this math. And he provides this upper and lower bound by doing polygons. And he could have taken this another step, right? He could have kept going. He could have done a 192nd size polygon. But really, he's limited by having to do all of this math, right? I'm sure it's very computationally expensive for him to do it, especially since, he didn't have a calculator. And so he ultimately stops at 96, decides that that's good enough for him. But how? So now we have to ask ourselves the question: how do we calculate pi today? Well, you might be wondering, why am I talking about pi? Well, pi is the ratio of the circumference of any circle to the diameter of that circle. Regardless of the circle size, this ratio will always equal pi. So if you remember what he was talking about before, that is exactly what Archimedes was defining. He was defining the ratio of the circumference of any circle to the diameter of that circle. He didn't call it pi because we hadn't come up with that notation yet. And so it's just interesting to see, and now that we've got that standardized, but before he just knew that there was a ratio and he wanted to figure out what it was. And so ultimately throughout history, we've seen a lot of people trying to tackle this. Some of them used ratios, some of them provide upper and lower bounds again, some of them just provide close enough estimates that they were useful. But you can see that it wasn't really until we started hitting, the 1500s that we started getting more and more accurate. And when this comes from a book is where I got this figure, which was made in 1998. And at that point, they had over 50 billion decimal places. And I don't know how many it is today, but I'm sure it is well beyond that now. But it makes you kind of wonder, well, how are we doing this? Are we creating polygons like Archimedes was? Well, not necessarily. So one of the things that we have, and one of the ways that we do it now, is we use summation. Using polygons like Archimedes did has a lot of serious shortcomings. And it was eventually discovered that you can sum an infinite series in order to calculate pi. One of the first people that did that was James Gregory, and he did this in 1671. And he found this summation here, where you keep incrementing the bottom by 2 each time. The problem with his method is that it is very computationally expensive. You have to take it out to several hundred fractions before you start getting just a couple of correct decimal places. It is a correct way of doing it, but it is very slow. A newer method that's often attributed to Isaac Newton is this one down here in the bottom. It's definitely a lot more of a complicated formula, but it is a lot more efficient and brings you to correct answers faster. And so, this is one of those things where Archimedes, he didn't have these ideas of these things that we have now. He had an idea. He wondered if he could use a polygon to describe it, and he took that and he ran with it, and he came up with a very good answer. If you look back, this is the decimal equivalent of what he did. If you calculate it out, and you can see that is in fact that pi is in between those, and that he was one of these first people to kind of come up with a good definition of it. And it's just fascinating to see how he did it versus how we do it now. It's one of the fascinating things that makes you wonder what new methods might we come up with in the future. Well, that brings us to the end of this 4-part series. I hope you enjoyed it. I hope you learned something and you had a little bit more curiosity. Again, please go take a look at some of the resources. I really had to pare a lot of stuff down and simplify a lot of things in order to get it to all fit. But this is a very fascinating thing and a very fascinating way of looking at the world through Archimedes' eyes. And so thank you again for watching, and I hope you have a great day.